So this is the last part, part 5 of chapter 8. And we're continuing on from part 4, where we had just started learning about the Lewis structures that do not follow the octet rule. So there were 3 types of Lewis structures that do not follow the octet rule. The first one was if there's an odd number of electrons. And your expectations for this class are that you know that that exists, but you're never going to be asked to draw the Lewis structure for any Lewis structures that have an odd number of electrons. So as far as you're concerned, if you're adding up the valence electrons and you get an odd number, you did it wrong. The second type, which you are expected to be able to do and that we talked about in part 4, is if there's less than 8 electrons around the central atom. So the only times that happens is when beryllium, Be, and boron, B, are the central atoms. And then beryllium will only have 2 lines around it, or 4 electrons, and boron will have 6 electrons, or 3 lines around it. Those are the only times we have less than 8 electrons around the central atom. Our third scenario is when there are more than 8 electrons around the central atom. And that's what this video is about. We're going to talk about those, and then I'm going to remind you really quick of something we learned in chapter 5 that applies to this. So the octet rule can be broken where the central atom can have more than 8 electrons around it if the central atom is in the 3rd row of the periodic table or lower, and if the formal charges indicate that the first structure you drew was not stable, but having more than 8 electrons around the central atom is stable. So again, the idea, 0 formal charges are great. 0 formal charges are good. We're trying to get a 0 formal charge. So the reason why, supposedly, that if you're in the 3rd row on the periodic table, that the central atom can have more than 8 electrons around it, is those elements have a d orbital. And their d orbital is not likely all the way full, like the next energy level d orbital. So those extra electrons, more than those 8 electrons, can go in there. So you ever thought about the octet rule? With electron configurations, 2 electrons can fit into the s orbital, and 6 electrons can fit into the p orbital. 2 plus 6 equals 8. That's where that magic 8 number comes from. Then on a certain energy level, the s and p orbitals can hold 8 electrons, and so they're going to bond, so that way they have 8 electrons. Except for the ones that have the available d orbitals. In that case, they're able to go above 8. So things like carbon, nitrogen, oxygen, fluorine, they can never break the octet rule. Even if they're the central atom, no matter what, they cannot break the octet rule because they're not in the 3rd row. So the example I have here, PCl5, there was no way to draw this Lewis structure without having 5 lines coming from phosphorus. Because first we'd add up the total electrons, and we put phosphorus in the middle. Then we'd connect it to all of the outside atoms. Well, there were 5 outside atoms. So right now, phosphorus has 10 electrons around it. Then we do the thing where we do the dots to the outside atoms, and then check the central atom, and it's like, does it have 8? Well, it has 10, actually. Now, if we check the formal charges here, all the formal charges of every single atom in this Lewis structure are 0. So this is an ideal Lewis structure. Things are happy in where they're at. Okay, so we're going to just practice. We're going to look at some other scenarios, but mostly we're just going to practice on recognizing when it's okay and when they should break the octet rule. Okay, so this is an example where it may not initially look like the molecule should break the octet rule, but it turns out that it does. So with PO4, 3-, phosphate, phosphorus has 5 valence electrons, oxygen has 6 each, and then there are 3 from the -3 charge. 24 plus, so 32 electrons. So if I were to draw this, I'm going to do it over here really tiny, and we're going to see that it's already on the slide, but put phosphorus in the middle, attach it to the oxygens. So I've used 8 electrons so far. Then I'm going to put dots around the oxygens. If I count, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 dots. Then we look at the central atom, and right now phosphorus has 2, 4, 6, 8 electrons around it. Everyone meets the octet rule. We've used all 32 electrons. Everything looks great. Like, this looks like a perfect Lewis structure. That would be wonderful. So if we look over here, that's the Lewis structure that's right there. So I'm going to erase mine because theirs is prettier than mine. In red over their Lewis structure are these tiny little numbers, and those numbers are the formal charge. So if we look at this Lewis structure, none of the atoms have a 0 formal charge. So none of the atoms are in a stable, steady arrangement. All of them are not ideal. So phosphate has a -3 charge. So it's not possible to get every single atom to have a 0 because there has to be a -3 total when I add them together. But in an ideal situation, we've got 5 atoms here, right? 4 oxygens and 1 phosphorus. Ideal would be 2 that are 0 formal charges and 3 that are -1 formal charges, because we're going to have to add up together to equal -3. That's not what's happening here. Now, once I do the formal charges and I recognize this looks crappy, I cannot break the rule. Like, I can't just go adding more electrons to things. We still have to use 32 electrons in our Lewis structure. But if the central atom, which is phosphorus in this case, is in the 3rd row or lower, we have the option of trying to do a double bond between one of the outside atoms and the central atom. The outside atoms can never break the octet rule, okay? So what they did in this example from here to here, they took this oxygen atom and moved 2 of the electrons over to right there. Now we have the formal charges that are shown. A -1, a -1, a -1, a 0, and a 0. That's the best this is going to get. 2 zeros and 3 -1s is definitely ideal.
Go.
So based on the formal charges, the second Lewis structure is definitely better than the first Lewis structure. So again, what we need to practice is how to know when you can do this, and making sure we understand if we recognize the formal charges are bad, what are the steps to try to make them better. Okay, so that's just explaining that. So what we're going to do now is we're just going to practice some. And actually H2SO4 is the first one listed. I'm actually going to do that one last. I want to do the other 4 first. I should have thought of that before now. But we're going to do ICl4-, XeF2, PO3, 3-, SbCl5. And then I actually have a couple more examples that I'm going to tack on here just as practice that I would have you do as practice during class. But since we're not in class, I'm just going to go ahead and do them. And if you are feeling comfortable and confident became one word, then as always, you can skip over stuff, but I'd rather have more examples available than less. So ICl4- is what we're going to do first. So when we draw our Lewis structures, we're going to still follow the steps we had before. ICl4-, we're going to add together the valence electrons. So iodine has 7. Chlorine has 7. There's 4 of them. And then I have to add 1 for that -1 charge. And then what I get is 36 electrons. Then I have to put the central atom in there. The central atom is the least electronegative element, which if we look at the periodic table and the trend, iodine is the least electronegative element. So chlorine, 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 chlorine. So we connect all the outside atoms to it. I've used 8 electrons so far.
Who are you talking to?
Hi, baby. I'm talking to my students. Okay. Thank you. So now we're going to add electrons to the outside atoms. Thank you. 2, 4, 6, 8, 12. Wait. Nope, I didn't count that right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 4 electrons left. So the outside atoms have their octet, and the central atom has its octet. So it kind of looks like, hey, we should be done. But the issue we have right here is there are 4 electrons left. We have to use those 4 electrons. And we have to use those 4 electrons in a way that does not break the octet of the outside atoms. Only the central atom can break the octet. So what we need to do is we need to check the periodic table for iodine, make sure it's at least in the 3rd row or lower, and it is. And then what we're going to do is, in this case, we're just going to add those 4 electrons to the iodine. We can't put them on the chlorines. So that means we can't make them as bonds, because if we made them as bonds, then, so like if I did this and put a line there, chlorine has 2, 4, 6, 8, 10 electrons around it. The outside atoms can never have thank you, baby, have more than 8. So if we look at our formal charges, because we should do that every time. I'm going to do it for chlorine once and then just write it for all of them because all the chlorines look the same.
Are you doing rainbow.
I'm just doing different colors. Here. 7 valence electrons minus 6 dots and 1 line. So 0, 0. Thank you, bud. 0, 0. Formal charge for iodine, 7 valence electrons minus 4 dots and 4 lines. -1, -1. So we knew that the formal charges wouldn't all be 0 because there's a negative charge in the molecule. Now, ideally, that negative charge would be on the chlorine because it's the most electronegative, but I've got no other way to draw this structure. Okay, so there's that one. So that one we didn't have to do double bonds or anything. It had more than 8 valence electrons because I had to use all the electrons and I had to put them somewhere, and the central atom is the only somewhere. So our next one is going to be XeF2. So 8 valence electrons for xenon, 7 for each fluorine, so that's 22 electrons. The least electronegative atom is xenon. Xenon, that's right, babe. And so I've used, let's see, 4. Sorry, I know we have an extra audience member today. So we're at 18 electrons. I'm going to fill, come on, bud. There. There.
There.
Are you my repeater?
There.
2, 4, 6, 8, 10, 12.
Oh, you did it wrong.
I did not do it wrong. Okay, so I have 6 electrons left. The outside atoms have their octet. The central atom only has 4. We have 6 electrons left. To get it to its octet, we would add 1, 2, 3, 4. So right now, all the atoms have 8 electrons. But the problem I have is there's still 2 electrons left over, and I have to use all of them. So in this situation, a lot like the last one, we have electrons we have to use, and we have to put them somewhere. We have to put them on the central atom because we're not allowed to put them on the outside atom. So I'm just going to go like that and just add them to the xenon. Now I want us to check formal charges to see what this looks like. So fluorine.
Green's my favorite color.
It's a good color. That's 0. That's 0.
Oh yeah, 0. Not my favorite number.
What's your favorite number?
3.
That's how many years old you are, isn't it? So 8 valence electrons for xenon minus 6 dots and 2 lines.
A number.
Okay. Okay, so I'm going to pause and find something for my little buddy to do, and then we're going to do more Lewis. Okay, so my little buddy is still here, but we're going to be quiet this time. Okay, so we're going to move on. I'm actually going to skip again. I want us to do Griffin. You didn't even make it 5 seconds.
That's funny.
You're not funny. Shh. Antimony chloride. So SB5. So this is 40 electrons. Okay, so the SB is going to go in the middle. I'm going to put the chlorines around it.
Let's see.
Shh, baby.
Free!
Griffin.
I found a free.
Griffin, this is the opposite of being quiet.
I found a free.
I know, and I'm proud of you.
I found a free.
All right, so I don't want to count all the dots. I did 6 on each atom, 5 atoms, so 6 times 5 is 30. So I have 0 electrons left. So if we look, I've used all the electrons. The outside atoms have their octet. The inside atom, the central atom, has 10 electrons, so that's breaking the octet rule. But there was no other way for me to connect all 5 chlorines except for doing this. So I'm going to check formal charge. So all the chlorines are the same. So 7 minus 6 dots and 1 line. 0, 0, 0, 0, 0. That's good. SB has 5 valence electrons minus 0 dots and 5 lines. That's good. So that Lewis structure looks glorious. Okay. So I want to go back to H2SO4, which was actually the first one that was mentioned. But it said H2SO4. And then next to it, it said all H's bonded to an O. This is the only situation that you're going to run into when it's not just one central atom and everything branching off of that. So we're going to explain that here in a second. First, I'm going to add up the electrons. So there's 2 hydrogens. There's 1 sulfur. There's 4 oxygens. So that's 32 electrons. If I go with the least electronegative element, and it cannot be hydrogen, so it's going to be sulfur. Okay, so when it says all hydrogens are bonded to an oxygen, it does not say the hydrogens are bonded to sulfur. So I'm going to draw the oxygens. Hey, robot. That's not a robot. So then the H's are bonded to an oxygen, so I'm going to pick 2 oxygens. Oh, why won't you write? And it can be any 2. And put those there. So I would have to tell you that statement. Let's count how many electrons I've used. So 2, 4, 6, 8, 10, 12. So now I'm going to worry about octets. So I put 8 around everything. So everything has 8. So I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I have 0 electrons left. And I've got my Lewis structure. So we got the weird thing where the hydrogens are attached, but I told you that was going to happen. So let's do formal charges. So this oxygen has 6 valence electrons, 4 dots, 2 lines. That's a 0, and I'm going to say that one's the same. This oxygen looks different though, so I'm going to do its formal charge. 6 valence electrons, 6 dots, and 1 line. So it's going to be -1. And this sulfur is 6 valence electrons, 0 dots, 4 lines, is 2+. Oh man, 2+ is bad, or +2. I could write it either way. So +2. That's really, 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 really bad. Okay, so I said a minus or a +1 is already not great, but if you get to a 2, things are super bad. So this Lewis structure is, I'm not done with it. Now, I don't want to mess with the oxygens that have the 0 formal charges because they're already the way that's best for them. So I'm going to look at the oxygens that have a -1 formal charge because they aren't quite the right arrangement yet. So what we're going to do at this point, sulfur is far enough down on the periodic table, it's allowed to violate the octet rule. I cannot just add more electrons to this Lewis structure. I have to use 32 electrons total, and I've already put them all in the picture. So all I can do is move them around. So what I'm going to do is I'm going to take 2 electrons that the oxygen has and move them to a bond. And then I'm going to double check formal charges and see if this was a good change or a bad change. So for that oxygen now, that oxygen is 4 dots, 2 lines, so that would be a 0. And sulfur now is 5 lines, so that's a +1. So that was a good change, right? We went from oxygen being a -1 and sulfur being a +2 to oxygen being a 0 and sulfur being a +1. So do you think that we can do this and make it any better? Well, yep, we can do the exact same thing, just with the other oxygen that's a -1. And then at the end of this oxygen looks like the bottom one. Sulfur is now 0 dots and 6 lines, 0. So this is one of those that you wouldn't immediately think that you need to break the octet rule, but based on formal charges, we did. Okay, so let's do PO3, so phosphite, PO3, 3-. So 26 electrons. I'm writing crooked apparently. P is in the middle. Oxygen, oxygen, oxygen. Oh, I didn't do a good job of counting my electrons, so we're going to stop and count electrons after this. So I used 6 electrons to draw lines. And then I used 2, 4, 6, 8, 10, 12, 14, 16, 18 to draw dots. And if we look at the central atom, it only has 6 electrons around it, so I'm going to put 2 dots right there. So now I'm to 0 electrons. Let's check formal charges. So oxygen, 6 valence electrons minus 6 dots and 1 line, so -1. And I'm going to do that on all of them since they're all the same. Oops. And phosphorus, 5 valence electrons minus 2 dots and 3 lines, which is a 0. Okay, so when we look at this, we've got 1 atom that's a 0 and 3 atoms that are -1s. If we go back and look at the molecule, we've got a -3 charge on it. So 3 atoms that are -1s is really the best case scenario. Spread that charge out a little bit all over the place. So phosphorus is an element that could break the octet rule. But in this case, right now, looks pretty good. So let's just say we didn't recognize that and we thought, well, let's try breaking the octet rule and see what happens. So what I'm going to do, I'm going to take this oxygen, I'm going to take 2 of its electrons and move them to a double bond. And then now I want us to redo formal charges. So phosphorus, when I do its formal charges, it still has 2 dots, but now it has 4 lines. So that makes this a -1. And this, 6 valence electrons, 4 dots, and 2 lines, that makes this a 0. So at the end of this, we still have 1 atom that's a 0 and 3 atoms that are -1. So all we did was kind of move the charge around. So we've got to decide, was this actually better or worse? So everything, we would like everything to be 0 if at all possible. In this situation, it's not possible. If we have to have a negative formal charge, we want it to be on the most electronegative elements. Oxygen is more electronegative than phosphorus. So this was actually a bad move. I'm going to erase this and this and this, put these dots back on, and go back to this being a -1 and this being a 0. So in this case, I'm actually not breaking the octet rule, but I wanted to show you that just because phosphorus can doesn't mean it always does. It's the formal charges that decide sometimes what to do with the octet rule. So that's why every Lewis structure you draw, I want you to write the formal charges for them. So we're just going to do a couple more examples. These are not necessarily breaking the octet rule. These are just, in some ways, trickier, maybe, than some of the others. So NO2F, I want us to draw the Lewis structure for that. So 5 valence electrons from nitrogen. Oh, hold on. 2 times 6 for oxygen and 7 for fluorine, so that's 24 electrons. We have pick the element that's in the central atom. So it's going to be the least electronegative, which if we look at the periodic table, nitrogen is the least electronegative. Okay, so I'm going to put, I've used 6. So putting electrons on the outside atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used all my electrons. We look at the central atom. The central atom does not have 8 electrons. Right now it only has 6, but I cannot add dots to it because I'm out of electrons. So I'm going to have to share. So at this point, I got to choose. Do I want to pick the fluorine or one of the oxygens? Initially, just go with one of them. Try one of them. And then what we're going to do is check our formal charges to see if that was good or bad. So I'm going to try an oxygen first. So now I want us to check formal charge. So fluorine, 7 valence electrons minus 6 dots, 1 line is 0. This oxygen is 6 valence electrons minus 6 dots and 1 line, which is -1. And this one, which is 6 valence electrons minus 4 dots and 2 lines, which is 0. And nitrogen, which is 5 valence electrons minus 0 dots and 4 lines, which is +1. So if we look at that, we've got 2 atoms that are 0, one that's a +1 and one that's a -1. So formal charge-wise, this isn't amazing. So you might think, well, when our formal charges look bad, one of the things we just learned to do was to do the expanded octet. Like, let's move some of the electrons on the oxygen and share them with nitrogen. But before we do that, remember, we've got to double check the elements on the periodic table. Nitrogen is not in the 3rd row. So that means this cannot violate the octet rule, because nitrogen is not in the 3rd row. So I can't move the electrons from the oxygen and share them with nitrogen, because if I did that, so let's just pretend like I did. How many electrons are on the nitrogen now? 2, 4, 6, 8, 10. Nitrogen can't have more than 8. So that's not allowed. So although these formal charges are crap, there's nothing else I could do. I could try moving that double bond over between the fluorine and the nitrogen, but what's going to end up happening is the fluorine's going to have a +1 charge, and that's not great. I want us to do SO2 Cl2. So the total number of electrons is 32. The central atom is going to be sulfur. So the way you put the oxygens and the chlorines does not matter as long as they're all there. So I've used 8 electrons so far. Is that 24? So I'm going to put dots on the outside atoms. So they each have 8 electrons on the outside atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used 24 electrons. So I have 0 electrons left. The central atom has its octet. So let's look at the formal charges. So oxygen, 6 valence electrons minus 6 dots and 1 line. So minus 1. Chlorine, 7 valence electrons minus 7 dots and 1 line is a 0. And sulfur, 6 valence electrons minus 0 dots and 4 lines is a plus 2. Crap, it's another one of those plus 2 things. That's really bad. So we cannot add any more electrons to this Lewis structure, right? We were at 0. We've used all of our electrons. So our only option is to move them around. But first, we have to check to see, can sulfur have more than 8 electrons? Because in the last example, nitrogen could not, so we had to leave it. So let's look. Sulfur is in the 3rd row. 3rd row, or lower, are the ones that are allowed to violate the octet rule. So if I go to try to fix this, I don't want to touch the chlorines because the chlorines have a 0 formal charge. I don't want to mess with them. They're already happy. I'm going to try to mess with sulfur, and I'm going to choose one of the oxygens because it was a -1. So I'm going to take 2 of the electrons and move it right there. Now I'm just going to check before I do that to the other one. I want to see, was this a good move or a bad move? So for the oxygen, it was 4 dots, 2 lines. That becomes a 0. For the sulfur, it's now 5 lines, so that becomes a plus 1. Hey, it went from 2 elements that are zeros, 1 that was a plus 2, and 2 that were minus 1, to being 3 elements that are zeros, and a plus 1 and a minus 1. That's better. But let's see if we can make it even better. So let's try that again, but with the other oxygen. I don't want to mess with the atoms that are already 0. Okay, so formal charge-wise. That last oxygen now looks like the first one, which is now a 0. I want us to look at sulfur. 1, 2, 3, 4, 5, 6 lines. So sulfur is a 0. So that's the correct form or Lewis structure for SO2Cl2. When you draw it first, you would just have a single bond between all the atoms. It uses the correct number of electrons. All the atoms have their octets. It looks great, but it's not until you do formal charges that you recognize not so great. So formal charges every time you draw a Lewis structure. And if you're having trouble with this, I can give you lots and lots and lots more examples. But I think for right now, I'm going to keep trucking. And if we need more examples, I'll be happy to make more examples. So the last thing in Chapter 8 is a reminder of something we talked about in Chapter 5. In Chapter 5, we were looking at energy, all the delta H's, and there were a whole bunch of different ways. It was 5 different ways to solve for delta H. We did things like Q equals M times C times delta T. We did the Hess's law where we flipped the reactions and add them together. We did products minus reactants. And then the last thing we did was bonds broken minus bonds formed. We've now talked about bonds. So I just want to remind you how this works. So bond enthalpy is delta H using bonds. So we saw this table in Chapter 5 where there were lots of different bonds with numbers next to them. Those numbers are how much energy it would take in kilojoules per mole to break one of those types of bonds. So we can see that every bond that has a different number. At the bottom, where it says multiple bonds, that's where we have double and triple bonds. And I think that it makes sense that a triple bond is more difficult to break than a double bond, and a double bond is more difficult to break than a single bond. But I want to point out, this is how much energy it takes to break a carbon-carbon single bond. This is how much energy it takes to break a carbon-carbon double bond. Notice it's not exactly twice the same. So it's a different amount of energy every time. So it takes energy to break a bond. If we form a bond, the amount of energy that we have is actually these numbers, but they're negative because we're putting them together, so it's releasing energy. Okay, so we did bonds broken minus bonds formed back in Chapter 5. So it's just in case you see that again. So I guess I'll write it down here. It was bonds broken minus bonds formed was how we could solve for the delta H of a reaction. Okay. So we talked about the bond enthalpy, bond length. I already mentioned that triple bonds are shortest, double bonds are next, and single bonds are the longest. This is just showing us a chart that not every single bond or double bond or triple bond are the same length, but we see that trend where triple bonds are the shortest and single bonds are the longest. We see that trend happen every time, but what we don't see are that every single bond is a different length. Every double bond is a different length. Every triple bond is a different length. And that's because the atoms are all different sizes. Oxygens are a different size than carbon. So when they share and they overlap, they're different distances apart. Okay, so it's all about size. But triple bonds are the shortest and single bonds are the longest. That's the end of chapter 8. Good and bad news. All of chapter 8 is going to move forward into chapter 9. Because what we're going to do in chapter 9 is take our Lewis structures that we learned how to draw and imagine them in 3 dimensions in what they look like in real life.